Okay, so good morning, good afternoon, good evening, wherever you are at the moment, to our second Maths of Climate seminar. So it's a great pleasure to have Nikki Vercauteren here. It's our second speaker. Nikki is from the Freie Universität Berlin, and her work is on the interface of metrology, dynamical systems, and time series analysis. And Nikki will talk about stably stratified atmospheric boundary layers today. It's the work for the past years. Before we get into the talk, just a few comments on the series. So the first one is about the general format, which is that we try to change the time zones. So for those of you who are now here and at a convenient time, there might be other seminars that you will be asleep during that time. So we try to cycle 9 a.m. London, 9 a.m. Beijing, 9 a.m. LA time. But all the talks are recorded. There's a YouTube channel. You can find out about it on the webpage. So the talk is recorded. So I want to make that clear too. And then just some rules. So we try to encourage questions also during the talk, just to sort of have a bit of lively interactions. So please type in the questions in chat. They will be monitored, and then from time to time we will kind of open up for questions. And also we try to use a software called Slido that Gemma will explain in a minute. And then, so Gemma, if you want to maybe explain Slido just before we start.
Okay, so Hannah's put the link in the chat. There's a code that you type in, and that should just bring you up to a website where you can enter in questions. I can just show you what that looks like. So you can type in your question here, you can put in your name or you can leave it anonymous if you prefer, and then you can upvote other people's questions. So if there's one that's very obviously popular, we know an ordering to ask them in. Yeah, and Freddie's pointed out we can also just type questions directly in the chat. Don't mind either way.
Okay, thanks, Gemma. So without further ado, Nikki, please.
Thanks. So let me first share my screen. Okay, so that should be fine, right? Looks all right.
Yep, perfect. Thank you.
Okay, so thanks to all the organizers, Georg, Gemma, Anna, Freddie for the invitations. Really fun seminar series. And as Georg said, I'm going to talk about the atmospheric boundary layer and turbulence parameterization, going through really a data-driven study. This is work done in collaboration with Slava Boyko and Sebastian Krumscheid, Slava being a PhD student in my group, Sebastian Krumscheid working at the RTWH Aachen. And so starting with the problem setting is we can look at climate models, and specifically if we look at the IPCC report, and we look at the 2-meter temperature, there's a lot of errors and inconsistency in the near surface temperature. We can see the error in the red color here. We can see really large errors around the pole regions and in high mountain regions. And also reanalysis inconsistencies, so between all the models that are used in the IPCC report, again, around the polar regions, we see the largest inconsistencies. And there's lots of physical processes and feedbacks in high latitudes and high altitude regions that are lacking understanding. My goal here is really to improve understanding of some of the physical processes in the models. And there's some colleagues here that have been taking apart the physical parameterizations that can lead to these errors and inconsistencies, and so that a large part is due to failure in the turbulence parameterization, which is specifically the one aspect that we're going to look at in this talk. And there's associated feedback processes. This is not the only one, but this is one of the aspects. And in high latitudes, there's also problems in representing mixing that's due to topography and interacting multi-scale processes. So I'm going to look at the stable boundary layer. What's the stable boundary layer? You have two broad types of boundary layer. Either if you think of daytime, you have sun warming the surface of the earth, you have thermals, and that triggers intense mixing. And if we look at the potential temperature profile, we have a well-mixed potential temperature that describes the turbulent boundary layer. If we reverse the situation and we look at nighttime or polar, look like snow surfaces, cold surfaces, then we have a cold surface atmosphere that's warmer, and we don't have this well-mixed temperature profile. Instead, we have a density stratification, and that leads to weak and intermittent turbulence. So the only trigger for turbulence in this case is the mechanical forcing, the wind shear at the surface. We don't have the thermals anymore. This is typically, this intermittent turbulence is a situation that's really challenging for models. And if we zoom in, we can even look at two distinct regimes of stably stratified boundary layer flow, which are broadly noted as the weakly stable boundary layers and strongly stable boundary layers. So what is this? In weakly stable boundary layers, we have a lot of wind shear, so mechanical forcing of turbulence is enough to sustain continuous turbulence. And what we use in model, namely similarity theory or Monino-Bukov similarity theory, is applicable. In a situation where the wind is weak, we have weak turbulence, calm nights, then this is typically when we have fogs and so on, and we'll have intermittent and non-stationary turbulence. And we have lots of instabilities that come and populate the boundary layer flow. And in these conditions, similarity theory is found not to be applicable anymore. So this is what we're going to look into and trying to find a fix for that using stochastic modeling ideas. So first, going back to basic ideas in weather forecasting models, if you want, turbulence closure models, they all assume a scale separation between the turbulence and the large scale forcing. So really the textbook picture is that you have, if you look at the energy frequency here and the spectral intensity, so if you want the energy, you have a peak of energy in the small scales that correspond to the turbulent eddies. Then you assume that there's this gap in energy, so there's not much activity at those scales. And then you have the so-called synoptic scales, the weather scales. And due to this scale separation, you can say, okay, let's make a turbulence closure that gives a statistical description of all this energy range here that equilibrates to this large scale forcing, the synoptic forcing. Now this is the textbook picture if you want. And if we look at data, we rarely observe such a gap in energy, a spectral gap. Instead, we really have a mixture of scales, and in the real world, we have surface heterogeneity. They lead to also multi-scale motions that do come also in the interface between turbulent and synoptic scales. We have non-stationarity simultaneously at multiple scales, and we lose this statistical equilibrium that turbulence closure rely on. And there's this sketch that was from Larry Mart's paper that shows the stability here and the scales of motion. And basically, qualitatively, you can think of this as you increase the stratification, the stability, the scales of turbulence decrease and decrease. And you have all these submeso scales, range of scales that get populated. So you have wave-like motions and different kind of motions. And instead of having this cascade from scale to scale, we also have direct energy transfers from large scale to turbulence, for example, or submeso scales to turbulence. This is in pictures what submeso motions can be. So here, a famous example in Van Gogh's painting is a Kelvin-Helmholtz instability. So you see lots of turbulence in this painting, but also this organized wave-like motion, which is a Kelvin-Helmholtz instability. Here, the same one in a picture. You have here probably gravity waves and clouds that organize alongside. These are all things where we know the physics behind it. We could developed models that are relying on the physical theory. But if you look at the two bottom pictures, these are from colleagues that did an experiment campaign where they released fog, artificial fog in the early morning hours, so stably stratified. And they basically did pictures and videos of what the fog was doing. And you see all kinds of, here a ram cliff motion, here some probably two solitary waves that collapse and or collide, I mean, and you have like a burst of mixing. And this thing, you don't, there's no hope, I think, to give a deterministic model for this kind of processes. They're just too all over the place and we don't know where they come from. And these are really small scale phenomena. So this is probably a 20-meter-ish scale on this picture. I'm not sure actually, but this is really small scale. So what do we have? We have scales of motion and they interact. And so if you look at this picture, for example, this is a tank experiment, a water tank, where there's increasing stability from A to B to C. There's a dye, so you can see the flow going from left to right. And you can see the first one has a shear layer, and you can see well-mixed boundary layer at the bottom. Then you increase the stratification, you see already more intermittent mixing, but still the mixing picks up and you have a well-mixed boundary layer. And in the last, like most stratified case, you have a Kelvin-Helmholtz instability that forms. It expands to a turbulent layer, and then you start having a full boundary layer. So you have a case where just the shear instability starts a mixing thing that reconnects to the surface, and you have a fully mixed boundary layer. So you can, what's happening in those very stratified cases, you have turbulence that can be triggered by such shear instabilities. It's typically discontinuous and detached from the surface. So in this example, it starts somewhere up and it reconnects to the surface after. Now the thing is, all our turbulence parameterization rely on the idea that we start having shear at the surface, friction at the surface, and we have a similarity theory that tells us, okay, the turbulence organizes in this log profile and it goes up to a certain height. So this is all surface-based. And in this idea that you have enhanced shear at some height localized in space, you can have a top-down process. So it goes against all our modeling ideas. So here the idea is to take a different approach. This approach, so I'm doing a data-driven study here. We're using multi-scale data analysis and time series analysis, non-stationary statistics, with the goal of getting some better idea of the physics behind this multi-scale interactions in the boundary layer. And so how do I organize this data-driven approach? Larry March wrote this really nice review paper showing basically that patching existing similarity theories has been attempted really a lot, but that has not fixed the problem so far. And he listed these questions that still need to be answered. And one is, when is turbulence generated primarily by submesoscale motions of the type I've shown in pictures? And also if intermittency of turbulence is connected to forcing by submeso motions. This is not completely clear. There's many reasons for intermittency of turbulence. There's question about the scale of shear instabilities and how we can estimate this from observations from field measurements of turbulence. And there's interest in having stochastic parameterization for submeso motions or their effect on the mixing. And so I've tackled this question looking at regime detection. So we're going to look at a clustering approach to detect periods where we see relationship between submesoscales and turbulence. We'll look at multi-scale data analysis to look at the scales responsible for transport in different clustered regimes of the flow, if you want. And finally, we'll look at stochastic parameterization, and this is work from Slava, where we'll finally look at ideas for stochastic scaling relationships that I'll talk about in more details. Okay, so data driven, so we need data, and we'll show here data from 2 field sites, namely one in Switzerland on this flat glacier. You can see here, it's an 8-kilometer flat glacier in Grand Montana. It's a ski resort in Switzerland. Stratification is really high, so here you have 2 vertical levels of measurements. They're separated by 70 centimeters, so really not much. And there's up to 5-degree difference between the 2 sensors, so it's really stratified. The other is this big vertical tower. It's a 30-meter high tower in Boulder, Colorado. That was a field campaign from NCAR. You have some mountain ranges, but the measurements are on the locally flat surface. And what we'll do is classify the boundary layer regimes by looking really at the regime-dependent statistic of submeso motion and their impact on turbulent mixing. So the classification is going to be based on scale interactions. We're going to find periods where we have causal relationships, statistically causal relationship between submeso scales and turbulence. Okay, so that's what the method does here. This is a method developed by Ilya Orenko. And we're modeling a time series. In our case, sigma W denotes the vertical velocity variance that we calculate on a time scale because we have time series measurements. So we take the vertical velocity variance on the scale of 1 minute. 1 minute because we found this to be really mainly turbulence. Everything that's happening on scales faster than 1 minute is really mainly turbulence. So we have a time series of this 1 minute variance. And then we want to know if the dynamics of the turbulence, so proxy here being the vertical velocity variance, if it's related to the activity of wave-like motions on submeso scales. And to look at that, we look at an external forcing in an assumed shape of a statistical model, where this U star here are time series of the filtered submesoscale wind velocity, where we look at a bandpass filter of the horizontal wind velocity on scales between 1 minute and 30 minutes, which is what we found to correspond to wave-like motions, what I called submesoscale motions. And so what we have in the model is a mean that depends on time and some linear model where we have a memory dependence. So we have the past few time steps of this submesoscale velocity. So the idea is if you have a shear acceleration on submesoscales, you'll see if the variance reacts to this time variation of the horizontal wind. And okay, so what's the time dependence here? We'll say we have this statistical model and we'll assume local stationarity of the model. And we'll fit, for example, a locally stationary model here on some time of this data, and then we'll jump to a different model, so different set of coefficients, and then maybe come back to this model and so on. So that's the clustering method. We're basically trying to cluster the data at the same time as we fit the optimal values of the coefficients. And I'm not going into how the method works, but this is, if you're interested in that, you can go to Eliad's paper here, where it's all explained. So we're using this on our turbulence data.
Nikki, may I ask you a technical question, please?
Yeah.
So here, what is the time step between the value, what is tau in your formula?
It's
the time step
1
between
minute. 1 minute. Yeah, so we have this 1 minute average vertical velocity. And the same thing here, we look at the bandpass between 1 minute and 30 minutes. So we really have one data point per minute.
And can you explain what clustering means? I mean, how does it work? I mean, at least qualitatively.
Yeah, yeah, sure. So basically, we're trying to fit the best possible model by allowing the coefficients to vary in time. But if they could vary at every time step, we could not solve the problem because we would have one set of coefficient per time step and it's over parameterized if you want. So the way Ilya suggested to solve this clustering problem is to say, okay, we'll assume that we stay in a fixed model, so a fixed set of constant coefficients if you want, for a while, and we have we use a bounded variation in the, well, we use a limitation on the number of transitions between the different models. So you say, for example, that you allow 3 different models, like I have on the example. So 3 different models means really 3 sets of values for the coefficients of your statistical model. And then you define the distance between the data and the model without the noise. And you minimize the distance with a constraint. And the constraint being that you can only jump so often between the different models. That translates into a constraint in your minimization problem. And Ilya reformulated this in using a framework of finite element method. So it's basically you reformulate your distance minimization in this minimization under constraint. And the constraint is reformulated by looking at the element, well, at an element space for where basically the coefficient lives, if you want. Or does this explain it enough? Or
yes, thanks a lot. It explains well the regime detection, I guess.
Yeah.
I also wanted to ask a question about this. Can I view this as like a sort of alike to Gaussian mixture models? So where they where now the statistics of these U stars at different different intervals, and then the B's just tell me which ones I choose.
Yeah,
so is this like a Gaussian?
Yes and no. It's the Gaussian mixture model has 2 very different things in compared to this. It's parameterized, so you assume a distribution of your data. You assume a set of Gaussians describing your data. Here, there's no distribution assumption, so it's a non-parametric model. And the second big difference is Gaussian mixture models do not have any time information in there. It's static. So it's really fitting the distribution. So it would be more related to hidden Markov model would be the parametric equivalent of this thing. But the main difference is we do not assume a distribution under the data. We only assume this statistical model form. And it's a really simple statistical model, but my question is really, when is turbulence mixing dynamically related to the dynamics of submeso scale? So I'm not trying to model the turbulence here. I'm really trying to understand the scale interactions. So the goal here is really to understand the physics, not to model the turbulence.
I also have a very quick question. Yeah. Sorry, Nikki. So like looking ahead to when you are going to implement this scheme in as a parameterization, do you have a particular like resolution of model or particularly time step, I suppose, in the model in mind?
I'll go to this in the second part of the talk, because I'm going to go to the parameterization actually. So if you can keep your question for the second part, that would be great. And so, so we've clustered the data according to this model I've just shown. As I said, it's really, really simple, but we have found 4 clusters of data. This is on the second data set I was showing, the FLOSS data, which was in Colorado. And what we look at here is what are the scales responsible for transport? How do we do this with wavelet decompositions? Technique called multi-resolution flux decomposition. It's essentially a wavelet decomposition. We take here the sensible heat flux. So we basically look at the vertical velocity variance, W, do a wavelet decomposition, look at the temperature, do a wavelet decomposition, and look at the co-spectra on each wavelet dyadic scale. What does it mean? We can read the figure like that. We have the amount of flux of turbulence, sensible heat flux, sorry, not turbulent, the sensible heat flux on the vertical axis. It's negative because we have stably stratified, so we go towards the surface. And we have averaging scale on the horizontal axis. You can understand that each scale, which would be one of the box plots, correspond to one wavelet scale. And it's the amount of flux transported by this particular wavelet scale. And if you were to integrate the curve here up to when it crosses the 0 line, you would have all the turbulence sensible heat flux. What it says is you have some box plots are here because we have many little windows of 30 something minutes in this one cluster, many windows in the second cluster, and so on. And we do box plots of this turbulent, of this heat flux co-spectra. And so the turbulent typically has, okay, for 0 averaging time, you don't transport any flux, any heat, but you have a most energetic eddy size that typically comes in this signature that you have a minimum or a maximum in your wavelet decomposition of the heat flux, the heat covariance here. And then you come back to 0. Why is that? It's because you come in the scale regime where you have waves, and waves do not transport temperature, linear waves. So if you follow linear wave theory, you do not carry temperature, so that's where you come typically to 0. We see this signature in this first cluster and in the second cluster, and these are sorted by increasing stratification, increasing stability. But what we see is the more we increase the stability, the more we reduce the turbulence contribution, and the more we increase the variability in what are the larger scales that correspond to the submeso scales. So these are on 10 minutes, 30 minutes-ish. The median is pretty much at 0, but the variability between single cases, so single hourly or 30-minute periods, I don't remember, yeah, it looks like it goes to an hour. The variability on single hourly flux transports is huge. And so in the most stratified cluster, the variability on the submeso scales is larger than the actually amount of flux of, due to turbulence, if you want. So for increasing stability, we have more flux due to submeso scales on individual hourly period, not on average. Then we looked at the statistical impact of the submeso scales by looking at the coefficients in the model very simply. So the coefficient give us a weight in front of these submeso scales. And if there's really no causal relationship between the two, then we should have more weight on the mean, if you want, and less on the B0 to BP. That's what we find by increasing stability. We go from relative weight. So when the mean is set to 1, the relative weight of the B0 to BP coefficients go from 0.04, so very small, to 0.3. It's not huge, but it's significantly more. And the variance explained by this statistical model, so the variance of the sigma W time series explained by this simple statistical model goes to 10% in the most stable cluster. So there's some significant relationship between the two. And these scales are typically not represented in models, as I was saying. So they have impact in the transport, and we need to somehow represent them. Okay, now if we look also at wavelet decompositions, if we look at the energy spectra, again, here in our 4 clusters sorted by increasing stability from left to right, we have 3 heights here, 30 meter, 15 meter, and 2 meter height measurement. We see a classical, so these are turbulent spectra with the wave number normalized by the height of measurements here. And we have the horizontal velocity spectrum normalized by the turbulent kinetic energy. And the lines show the median between all our cases and the quantile, 25th and 90% quantiles. We see in the weakly stable clusters, we have a typical inertial subrange with a maximum and then less energy that would correspond to this gap, like spectral gap we looked at the very beginning. But the more we increase the stability, the less we see this spectral gap. Instead, we increase the energy going from the turbulent scales to the submeso scales continuously. And what's interesting is we see we have more and more scatter in our data. The spectra do not scale anymore. So we lack this scaling. And so we lose the scale separation, and we lack the statistical equilibrium then. So we have this submeso scale forcing. This is the same thing on the vertical velocity component. We also see this huge scatter in the most stable cluster. So I interpret this result really as we lose the scale separation between turbulence and submeso scales. We also lose the statistical equilibrium. So to summarize, and I put in gray what we have results for, but I didn't show in this talk. But basically, we looked at many things in the strongly stable flow regimes, and we saw that what I showed here, that we have transports mainly by submesoscale motions in the really most stratified cases. We have lack of equilibrium of turbulence and probably direct energy exchange between submesoscale and turbulence. We've looked at it also with other type of wavelet decomposition that I haven't shown. We've classified all kinds of submesoscale motions where we saw statistics of them. We tried to relate them to terrain. It looks like it's very controlled by local topography, but it's so different from site to site. It looks pretty much random, and so this is good for stochastic modeling, but this is challenging for parameterization. And the challenge now, and I'm going to go to parameterization, is to know what to do with all this qualitative understanding and have some kind of quantitative models. Okay, so if you have questions before I go to parameterization, go ahead. Okay, so how do we want to do this stochastic modeling? Now I'm going to the basic turbulence parameterization in weather forecasting and climate models. Typically, you say turbulence is a kind of diffusion process, and we take a flux gradient relation. So written here, for example, for the momentum flux, so we have U and W being the streamwise and vertical wind component, the prime being the deviation from the means, bar mean the mean. So we have the horizontal momentum flux here, which we represent as just a counter gradient thing. So we have the gradient of the mean wind velocity, and we have some Km, which is our turbulence diffusivity. So what does a turbulence parameterization do? It basically gives a model for this turbulent diffusivity. So what it uses basically is the Prandtl mixing length concept, which says, okay, eddy viscosity is proportional to a velocity and a characteristic eddy length scale. So we have Km with our velocity and length scale here. Sorry, I should have something in front of my equation, but you can see it better than me. So, and we'll look at a closure where we use the turbulent kinetic energy to scale this, this mixing coefficient. So we have a constant times the square root of the TKE, which is our velocity scale and the length scale. And now come the Money-Nabokov similarity theory part. We need some adjustment to account for the impact of static stability. And this comes through so-called stability functions. So essentially you say you take your length scale, and I'm giving the example here of a so-called 1.5 order closure, meaning we have a prognostic equation for the turbulent kinetic energy. And the rest is only first order, meaning we have this gradient models with the Km, if you want. And so this length scale is then parameterized as kappa, which is the von Karman constant, the height, and we modify it with the stability function. So qualitatively, if you want, the idea is to say we have a neutral situation, no static stability, we have a log profile. And in unstable, we need to modify this log profile to make it a bit steeper. And in stably stratified, we need to flatten it a little bit. This is what the stability functions are doing. And what's the Richardson number? This is the scaling, the non-dimensional number we use for the scaling. And this is the Richardson number. Here I write it in this gradient form, if you want, bulk gradients, where we have the thermal stratification here. So these are the buoyant forces that damp or generate turbulence, depending. And here we have shear generating turbulence. So it's really this, on the one hand, you have the static stability effect, and on the other hand, you have the mechanical forcing, and this Richardson number tells you the relationship between the two.
Okay, I have a question.
Yeah.
So in these phenomenological models, how well have they been tested from empirical measurement?
So the stability corrections, they've been tested on lots and lots of data. This is really what Monino book of similarity theory was about. And they've been tested on many, many field campaigns, and these are ad hoc functions that have been fitted on years and years of measurements. And so I can show you actually, the next picture shows how it works on our data set. There's many studies that show basically all the same thing in tons and tons of data sets. Works well for weak stability, works okay, it works really well in close to neutral. Very convective, you start having problems, and very stably stratified, you have problems. And this is what we see here. So we have the stability function calculated from our data. So, and we have the Richardson number here. And the little curves here are showing the exact formulation used in this ECMWF model and in the Canadian metrological model and at the Met Office. You can see they're all very similar because they're all fitted on more or less the same data. Here, the data points are the colored points. The color scale encodes the height of measurements because we had these 30-meter towers. And I think blue was the closest to the surface and green is the 30-meter. We divided here, we look at only cases with the wind speed at 30-meter is larger than 8 meters per second. You can see the curves are fitting the data quite well. For smaller than 8 meters per second, you have this huge scatter and it goes all over the place. And this is really what you see in all these measurement campaigns. So this is what people acknowledge when they say Monino book of similarity theory does not work in strongly stable condition. This is this scatter, one of the things. What's the vertical line here is the critical value of the Richardson number, which we use here as 0.25, which is often used as a threshold in model to say, okay, let's shut down the turbulence here or add some, rather add some mixing above this value to avoid having laminar flows, which is not physical. And what we see is what I've discussed. We see huge scatter for high stability, which is large, high values of the Richardson number. And this is where the scatter is probably related to intermittent turbulence and submesoscale motions. And this is where we want to define a stochastic stability function relying on this framework, the clustering framework, that now needs some extension. And this is what we've been working on with Slava mainly, has been working on with Sebastian and I. So what's our stability function to model? This is this phi function, which basically written slightly differently from before. We have our kappa times z, that was the von Karman constant, the height. We have our gradient, and here we just use u star, where we had the TKE before. It's just u star is the surface momentum friction. Same thing, it's just another scale if you want, but it's still a velocity scale. And so we have this stability function and we have data, so we measure it. That was the little points on the figure just before. And now comes the stochastic model. We assume a stochastic differential equation to represent basically all these points that we have here. So we'll have this model that is now not this function of the Richardson number anymore, but will be a stochastic differential equation where we hope it can cover the distribution of all these points. But it's a dynamical function now. And so we suggest a stochastic differential equation form. Slava has been trying quite many forms. And the idea is to say we want it to relate to the Richardson number because this is the physical scaling value that we expect to play a role. But we basically allow some nonlinearity in our model, and we allowed some noise, here multiplicative noise, to have the intermittency that we observe. And our sigma here is a variance. We have a hat here to say that would be the proxy for the submesoscale variance. So all these submeso motions. And the thing is, we want now, instead of learning the coefficients of the time series model that I showed before, we learn now the model coefficient of this assumed shape, make the coefficients now unknown, this sigma and this Richardson number, we make it all unknown. And we want to learn this from our data. How do we do this? With some kind of maximum likelihood estimator, but it's tricky because you can't really do a maximum likelihood estimation on the stochastic differential equation. But luckily, some smart people have found a way to do it numerically by reshaping your stochastic differential equation in something that looks more like a white noise process, if you want. So first transforming your equation and then doing some expansion using Hermite polynomials to approximate numerically your maximum likelihood estimator. Read those papers if you want to know more. I cannot really tell you more about this, honestly. But basically, we use this maximum likelihood estimator to reformulate this minimization problem we had in the statistical clustering before. So we extend the FEM clustering, the FEM-BV-VARX clustering that we saw before from Ilya Orenko, to this FEM H1, H1 being now the space where we use our function for basically the clustering for the so-called affiliation function, which is this gamma here, which tells us in what cluster we are. So in what values of the coefficients of the stochastic differential equation in our case. And so what do? We have now this clustering functional that we want to minimize. So it's what we had as distance between the data and the model before. So it's still the distance, if you want, between the data and the model. But instead of using a distance, we have this log likelihood for the specific SDE, nonlinear SDE that we're looking at. And gamma here is our cluster affiliation function. So it's basically a number between 0 and 1 that gives us the probability to be in cluster K at time Ti. So we have this log likelihood for the SDE, and we say our model will have some slow variation of these theta coefficients, the theta coefficients being the coefficients in the SDE. And the dynamics is then on this fast scale with the time-dependent values of the coefficients. So same principle as Ilya's clustering method, but the big difference is here it's a time-continuous model. So you don't have the discretization question anymore, and you can plug some kinds of nonlinear SDEs into this framework.
So Nelly, you have two questions.
Yeah.
One is a general question by Stephanie. And Stephanie, would you like to ask your question?
I can so. So as Freddie said, it is a general question. Are these similarity theories only valid or validated on flat surfaces?
Sorry, on what surfaces?
On flat surfaces.
So it's for now this modeling thing that I'm showing, we've only done it on one field side. So I cannot really talk about validation apart from this one data set that I'm looking at. And so your question is really on the boundary layer modeling or not on.
I was thinking about the similarity theory in general, if it's only valid on above flat.
Oh, okay. The similarity theory is defined for homogeneous flat surfaces and is known to break down in complex terrain. There's some fix to account for heterogeneous terrain by doing some tiling, so-called mosaic approach, where you say you have patches where you assume local homogeneity and you patch them together to have transformation of the similarity theory. But generally, heterogeneity gives problems, and this is what we believe is connected to this scatter in the stability function. We don't have this homogeneity. So this intermittency, scatter, and everything is partly related to non-stationarity in time and partly related to heterogeneous terrain. And we say, okay, let's, instead of trying to know as much as we want about the terrain and represent this variability of the terrain, because we don't know how it relates to the turbulence yet, we try and ignore this and use a stochastic model instead to replace for the lack of physical understanding. But the validation is, we would need to do many field studies.
Your method also in kind of mountainous terrain?
Yeah, that would be good to test, but I believe in really mountainous terrains, what one wants to do some things deterministically as well, because there's things that are very organized with the mountain that doesn't change in time if you want. So you'll have slope flows and everything that you can do better than a stochastic model on that. So the question is how to sort out the data to know exactly what to look at in the stochastic aspect. And that I haven't looked at yet. But that's definitely an important thing to look at, because we can't do everything with stochastics. There's really, as I said, the slope flows stay every day, and you can do better. And many people do very good modeling approaches for those.
And you have another question, Nikki, by Valerio about your stochastic model. Valerio, do you want to ask your question? Valerio Lambo.
Yeah. Hi, Nikki. My question is as simple as what I wrote, and probably even a bit trivial. How large is the mistake that you make if you assume that the distribution of your stationary parameters is Gaussian? Because you mentioned that you start from a white noise and then you do something with your numerical MLE.
Yeah, it's just when you have this nonlinear SDE shape, if you have your DW that would be the Wiener process, then the distribution of phi is not Gaussian. So basically, and this is work by this Ait Sahalia and Sebastian Krumscheid, where they show you can transform this SDE to make it into a form where you basically have just a Wiener process here. And then you can have a Gaussian distribution-ish for your stochastic process. So it's just, you make an error because you lose Gaussianity because of the multiplicative noise in your thing. You have nonlinearity that changes your distribution. So if you use Gaussian assumption for your maximum likelihood estimator, you're wrong. It's just the wrong distribution.
Okay, and it's very far from what you actually get. That's what you mean.
I guess it depends on the actual degree of nonlinearity in the model, but really I'm no expert here. I don't think I can give you anything more quantitative.
Okay, thanks.
You're welcome. Yes, so basically that's the thing. We assume this, and the shape of the model is chosen so that we can have intermittency due to the nonlinearity, the multiplicative noise, and so on. And so we start with exactly this form of the model. As I said, Slava tested different kind of nonlinear models and found this to work pretty well in our data set. Still have to test it on different data sets. So we have basically this lambda coefficient, V coefficient, and sigma are the one that we need to fit on our data with the maximum likelihood approach and the clustering from the FEM-H1 SDE clustering. And the time variation is now this cluster affiliation dependence. And what did we look at? We fitted this on the data set that was the FLOSSII data set, the one in Colorado. So we have these 7 measurement heights that are shown in color here. And what we show here is the scaling of the model parameter, lambda, V, and sigma with the log of the Richardson number. And what's really nice is you see a really nice scaling of the learned model coefficients with this Richardson number, which is something we have in weather forecast models and in climate models. This is what we use in our normal stability function. So here we see this scaling, which means instead of fitting the function, we can fit the SDE, having a closed form expression fitting this curve for lambda, v, and sigma on the Richardson number. How does it work? And this is my last slide. So we have this fitted function that where the kappa and epsilon and sigma here are the functions that were fitted here, the red curves. So they're ad hoc fitted on this data here. And if you simulate this stochastic differential equation, which is now a closed form model because we know our I, the Richardson number, and we know the functions, we have a stationary distribution of the stochastic differential equation, and you have some level sets of the distribution shown in black here. So it's 0.01 here, 0.05 here. So these are all the level sets of the distribution. You can see it fits the data really well. The expected value is in red. So you can see, and the dotted line here is one of the stability functions that we were looking at from the classical weather forecasting models. So this is the Canadian model. So what do we see? The expected value follows this line pretty much until the critical value of the Richardson number, and then it doesn't anymore. And the yellow is the maximum of the distribution. You can see the strong non-Gaussianity by looking at the difference between the expected value and the maximum of the distribution. So we actually match the distribution for these data sets quite well. So that's my conclusion. I've shown you how to use this clustering method to extract information from the field campaigns we looked at, with the idea of modeling intermittent turbulence and mixing also due to submesoscale motions. We saw that the impact of submesoscale motion is strong in strongly stable regimes. I mentioned this lack of scale separation between the turbulence and the submesoscale motion, and the consequence being the non-equilibrated turbulence. And we see first signs of scaling relationships for the parameter of a stochastic stability function, or a stochastic stability relationship, whatever you want to call it. And so what I think we should do as next step is to try and look at more field sites, more measurements, to see how robust these stochastic scaling relationships are from different data sets, and also to look at the heat diffusivity. Now, what I've shown you so far was only on the wind, the momentum. So we could try and have a coupled system to look at the relationship between heat transfers, so basically potential energy and kinetic energy of turbulence. And that's all I had. Thanks.
Thanks a lot, Nikki.
Thank you very much, Nikki, for this 2 or 3 time series analysis and then modeling. Fantastic. Thank you so much. So I will, for this session, I will stop the recording now so that people might feel even more comfortable asking questions.